The cosmic scale, understanding Earth's true size in the universe. Have you ever wondered just how small Earth really is? Not compared to your house or your city, but compared to everything that exists? Tonight, we're going to take a journey that will completely transform how you understand your place in existence. We're going to explore the actual scale of Earth against the backdrop of the cosmos, and I promise you, by the time we finish, you'll never look at our planet the same way again. Most people have a vague sense that Earth is small compared to the universe, but the reality is far more extreme than you probably imagine. Earth isn't just small, it's so incomprehensibly tiny that finding adequate words to describe its scale becomes nearly impossible. We're going to change that tonight. We're going to give you a real understanding of where we stand in the cosmic order. Before we begin, if you appreciate deep explorations of space and cosmic perspective, hitting the like button or subscribing would really support this channel's growth. It's a simple action, but it genuinely helps. Now, let's start our journey into scale. Earth, our starting point. Let's begin where we are. Earth, our home planet, the ground beneath your feet right now. From our human vantage point, Earth seems massive. You could dedicate your entire existence to exploration and still leave vast regions unexplored. The continents span thousands upon thousands of miles. Oceans blanket approximately 71% of the planetary surface. Mount Everest towers nearly 6 miles into the atmosphere. To our ancestors, Earth represented the entirety of existence. The heavens above were merely a celestial dome adorned with luminous points. The ground below extended infinitely in every direction, flat as far as anyone could determine. This worldview made perfect sense given their observational capabilities. When you gaze toward the horizon, Earth appears flat. The curvature is too gentle to detect without achieving significant altitude. Earth measures approximately 7,926 miles in diameter at its widest point. Imagine attempting to walk Earth's equator, somehow managing to traverse the oceans. At a steady 3 miles per hour, walking 8 hours daily, you'd require roughly 3 years and 1 month to complete the circuit. That's an extraordinarily long journey. Earth's surface encompasses about 197 million square miles. To put this in perspective, if you could visit every single square mile and spent merely 1 second at each location, the journey would consume over 6 years of continuous travel without rest. The United States, among the world's largest nations, covers approximately 3.8 million square miles. That represents less than 2% of Earth's total surface area. But here's where our perception begins shifting. When we start comparing Earth to other celestial objects, when we zoom out even slightly, Earth begins shrinking. Not physically, of course, but in relative significance. Earth transforms from everything into merely one thing among countless others, and as we continue pulling back our cosmic camera, Earth becomes smaller and smaller until it approaches invisibility. The Moon, our closest neighbour. Our first comparative stop takes us to Earth's only natural satellite. The Moon orbits our planet at an average distance of approximately 238,155 miles. That's roughly equivalent to circling Earth's equator 9.5 times. By human standards, this distance is genuinely vast. When Apollo missions travelled to the Moon, the journey required about 3 days. The Moon itself spans roughly 2,259 miles in diameter. That's approximately 27% of Earth's diameter. So yes, the Moon is smaller than Earth, but not dramatically so. If you imagined Earth as a basketball, the Moon would approximate a tennis ball in size. But here's what's genuinely interesting. The distance separating Earth and Moon equals about 30 Earth diameters. Picture lining up 30 planet Earths between us and our satellite. That's the actual amount of empty space in that gap. Most people don't realize this truth. When you encounter images showing Earth and Moon together, they're typically depicted far closer than reality. The truth is that enormous amounts of nothingness separate us from our nearest cosmic companion. This represents our first hint that space consists primarily of emptiness. Even in our immediate celestial neighbourhood, distances dwarf the objects themselves tremendously. The Moon's relationship with Earth is actually quite unusual within our solar system. Most moons are minuscule compared to their parent planets, but our Moon is proportionally large. In fact, astronomers sometimes refer to the Earth-Moon system as a binary planet, because the Moon is so substantial relative to Earth. The Moon's size produces tangible effects on Earth, It generates the tides we experience daily. The moon also stabilizes Earth's axial tilt. Without it, Earth's axis might wobble chaotically across time, triggering extreme climate fluctuations that could render complex life difficult or impossible. Viewed from Earth, the moon appears roughly the same size in the sky as the Sun. This is pure coincidence. The Sun is approximately 400 times larger than the moon, but it's also roughly 400 times more distant. This coincidence creates total solar eclipses where the moon perfectly obscures the solar disk. The moon is also gradually receding from Earth. Each year it drifts about 1.5 inches farther away. This occurs because of tidal interactions. Billions of years ago, the moon orbited much closer, and Earth's day lasted perhaps only 5 hours. For now, the moon remains our closest companion in the void. And in 1969, humans set foot on its surface for the first time, demonstrating what becomes possible when we expand our exploratory boundaries. The Sun. Where Earth truly begins to shrink, now let's turn our attention to the Sun. The Sun is why we exist. Without its radiation and thermal energy, Earth would be a frozen sphere hurtling through darkness. But the Sun is also where Earth's dimensions truly begin to seem insignificant. The Sun has a diameter of approximately 864,000 miles. That's 109 times Earth's diameter. The Sun's volume is so tremendous that roughly 1.3 million Earth-sized spheres could fit within it. Consider that carefully. Every mountain, ocean, city, and person who has ever existed, all of human history, occurred on a planet whose volume represents less than 1/1000th of the Sun's interior. The Sun contains 99.86% of all mass in our solar system. Everything else, every planet, moon, asteroid, and comet combined, comprises only 0.1%. The Sun dominates our cosmic neighborhood absolutely. The Sun is also approximately 93 million miles from Earth. We call this distance one astronomical unit, or AU. Light from the Sun requires about 8 minutes and 20 seconds to reach us. If the Sun vanished suddenly, we wouldn't know for over 8 minutes, because the light carrying that information would still be travelling toward us. To grasp this distance, consider that a car maintaining highway speeds would need 176 years to traverse this 93 million mile gulf. The fastest spacecraft humans have constructed, the Parker Solar Probe, requires months to reach the Sun, even while travelling at speeds exceeding 400,000 miles per hour at closest approach. The Sun is actually quite ordinary as stars go. Astronomers classify it as a G-type main sequence star, sometimes called a yellow dwarf. It's approximately 4.6 billion years old, roughly middle-aged. It contains sufficient fuel to continue burning for another 5 billion years or so, before beginning its death process. The Sun's power output is staggering. Every single second, it converts roughly 600 million tons of hydrogen into helium through nuclear fusion. This process releases tremendous energy. The Sun generates more energy in 1 second than all of human civilization has produced throughout its entire existence. The Sun's surface maintains a temperature of approximately 10,000 degrees Fahrenheit. The core, where fusion occurs, reaches about 27 million degrees Fahrenheit. The pressure at the core equals roughly 260 billion times Earth's atmospheric pressure at sea level. The Sun also produces solar flares and coronal mass ejections, enormous releases of energy and matter from the Sun's atmosphere. When directed at Earth, they can create beautiful auroras near the poles, but they can also disrupt satellites, power grids, and communications. Contemplating the Sun reminds us that Earth is not the centre of the solar system. For most of human history, people believed Earth occupied the centre of everything. It required brilliant thinkers like Nicholas Copernicus and Galileo Galilei to demonstrate that the Sun was actually central, with Earth orbiting it. This represented humanity's first major lesson in cosmic humility. The solar system, our cosmic neighbourhood. Our solar system extends far beyond Earth and the Sun. Let's zoom out and examine where Earth fits in this larger structure. The inner solar system hosts the rocky planets. Mercury hugs closest to the Sun, alternately baked and frozen in its extreme orbit. Venus follows, shrouded in toxic atmospheric clouds. Then comes Earth, our blue sphere at the optimal distance for liquid water. Mars completes the inner worlds, a cold desert that once hosted flowing rivers. These 4 terrestrial planets cluster relatively close to our star, all within about 1.5 times Earth's distance from the Sun. Between Mars and Jupiter stretches a vast region populated by the asteroid belt. This zone contains thousands upon thousands of rocky fragments, the building blocks that never quite coalesced into a planet. The largest series spans only about 580 miles. More than 13 series could line up side by side across Earth's diameter. Despite containing millions of objects, the asteroid belt is predominantly empty space. If you flew through it, you'd likely never see an asteroid with the naked eye. The distances between them dwarf their tiny sizes tremendously. Then we reach the realm of giants. Jupiter dominates the outer solar system like a monarch surveying its domain. With a diameter of approximately 86,181 miles, it's about 11 times wider than Earth. Jupiter's volume is so immense that 321 Earths would barely fill it. This planet is massive beyond easy comprehension. It contains more mass than all other planets combined. If Jupiter were a hollow sphere, you could fit every other planet in the solar system inside it with room to spare. And yet Jupiter itself is tiny compared to the Sun. About 1,000 Jupiters could fit within the Sun's volume. Saturn follows Jupiter in the outer solar system, nearly as impressive in scale. With a diameter of approximately 72,367 miles, Saturn could swallow 764 Earth-sized worlds within its bulk. But Saturn's most distinctive feature isn't its size, it's the magnificent ring system encircling it. Made of countless particles of ice and rock, these rings extend tens of thousands of miles from the planet's surface, yet they're remarkably thin. If you scaled Saturn down to basketball size, the rings would be thinner than paper. The ice giants, Uranus and Neptune, dwell in the cold darkness beyond Saturn's orbit. Both are smaller than Jupiter and Saturn, but still dwarf Earth. Uranus's volume equals roughly 63 Earth-sized planets, while Neptune's interior could accommodate 57 Earth-mass bodies. These distant worlds require decades or centuries to complete a single orbit around the Sun. Neptune, the most distant planet, needs 165 Earth years just to make one circuit around our star. Beyond the planets lies the Kuiper Belt, stretching from Neptune's orbit outward for billions of miles. This region is filled with icy bodies left over from the solar system's formation. Pluto, once considered our 9th planet, resides here among thousands of similar frozen worlds. Pluto is only about 473 miles across. About 5.4 Plutos could line up across Earth's diameter. The Kuiper Belt represents a vast reservoir of primordial ice, a frozen archive of materials from the solar system's birth. But even the Kuiper Belt isn't the true edge of our solar system. Far beyond, almost incomprehensibly distant, lies the Oort cloud. This vast spherical shell of icy objects surrounds our solar system like a cosmic bubble. It begins at about 2,000 times Earth's distance from the Sun and extends outward to nearly 2 light-years. That's almost halfway to the nearest star. The point is this: our solar system is vast. It extends for trillions of miles, and in all that space Earth is one small rocky planet orbiting at a distance that's relatively close to the Sun. In a proportional model where the Sun equals a basketball's diameter, Earth would measure no larger than a peppercorn positioned 26 feet. Distant, the nearest stars, where distance becomes incomprehensible. Now let's leave the solar system and venture out to the nearest stars. This is where distances become so large that our usual measurements stop making sense. The nearest star to our Sun is Proxima Centauri, part of the Alpha Centauri system. It's approximately 4.24 light-years away. A light-year is the distance light travels in 1 year, which is about 5.88 trillion miles. So Proxima Centauri is roughly 25 trillion miles away. Here's a way to visualize this scale. Remember how the Sun is 93 million miles from Earth? Proxima Centauri is about 268,000 times farther away than the Sun. If the distance from Earth to the Sun was 1 inch, the distance to Proxima Centauri would be about 4 miles. The Voyager 1 spacecraft, launched in 1977, is currently humanity's most distant object. It's been travelling for over 47 years and is now about 15 billion miles from Earth, moving at roughly 38,000 miles per hour. At that speed, Voyager would still need 73,000 years to reach Proxima Centauri. And it's not even aimed in that direction. Even with hypothetical future technology, if we could build a spacecraft that travelled at 10% the speed of light, which is far beyond anything we can currently achieve, it would still take over 42 years to reach Proxima Centauri. The distances between stars are genuinely almost incomprehensibly vast. And here's the thing. Proxima Centauri is our closest neighbour. Most stars are much farther away. At these scales, Earth doesn't just shrink. It vanishes completely. If you were at Proxima Centauri looking back toward our solar system, you wouldn't be able to see Earth at all. Even with a powerful telescope, the Sun would be visible as a bright star, but Earth would be lost in its glare, a tiny dot too close and too faint to detect. Proxima Centauri is a red dwarf, the most common type of star in the galaxy. It's much smaller and cooler than the Sun. Its diameter is only about 129,000 miles, roughly 14% of the Sun's diameter. It has only about 12% of the Sun's mass. Because Proxima Centauri is so small and cool, it burns its fuel very slowly. It will keep shining for trillions of years, long after the Sun has died. In fact, no red dwarf anywhere in the universe has ever died of old age. The universe isn't old enough yet. Proxima Centauri is also a flare star. It regularly produces powerful flares, sudden releases of energy that can temporarily increase its brightness. These flares would be bad news for any planets hoping to host life. Interestingly, Proxima Centauri does have at least 2 known planets. Proxima Centauri b orbits in the star's habitable zone, the region where liquid water could exist on a planet's surface. But given the flares and radiation, life there seems unlikely. Beyond Alpha Centauri, the next nearest star is Barnard's star, about 6 light-years away. Sirius, the brightest star in Earth's night sky, is about 8.6 light-years away. Betelgeuse, one of the most famous stars, is about 700 light-years away. It's a red supergiant so large that if you placed it where the Sun is, it would extend past the orbit of Mars. All these stars are part of our stellar neighbourhood, and yet the distances between us and them are so vast that we'll probably never visit them. The light you see when you look at Betelgeuse left that star around the time the Crusades were ending on Earth. And our planet at these distances has disappeared from view. The solar system itself is just a point of light, and Earth is far too small and faint to be visible within that point. The Milky Way, our galactic home. Let's zoom out further. All the stars we can see with our naked eyes, every single one, belongs to our galaxy, the Milky Way. The Milky Way is a spiral galaxy containing somewhere between 100 billion and 400 billion stars. Our Sun is just one of them. The Milky Way is approximately 100,000 light-years across. Remember, Proxima Centauri is about 4.24 light-years away. The width of our galaxy is about 24,000 times that distance. If the distance to Proxima Centauri was 1 inch, the Milky Way would be about 2,000 feet across. That's taller than most skyscrapers. Our Sun sits about 26,000 light-years from the galactic centre. We're in a minor spiral arm called the Orion Spur, about halfway out from the centre. We're not in the middle of anything special. We're in the galactic suburbs, in a relatively quiet region where stars aren't too densely packed. At this scale, Earth's presence in the cosmos becomes conceptually different. Even our entire solar system is just a tiny point. The Sun, which seems so massive compared to Earth, is now just one ordinary star among hundreds of billions. And Earth? Earth is far too small to even register. Imagine compressing our galaxy into a structure 100 feet across. Our entire solar system would measure thinner than a human hair's width, and Earth would be far, far smaller than that. At this scale, Earth wouldn't just be invisible, it would be smaller than an atom in the model. The Milky Way is a barred spiral galaxy. This means it has a central bar-shaped structure made of stars, with spiral arms extending from the ends of the bar. Our Sun is located in the Orion Spur, which is actually a minor arm connecting 2 major spiral arms called the Sagittarius arm and the Perseus arm. The galaxy rotates, but not like a solid wheel. Different parts rotate at different speeds. Our Sun takes about 225 million years to complete one orbit around the galactic centre. This is called a galactic year or cosmic year. Think about that. In the time it takes for our Sun to go around the galaxy once, entire species rise and fall on Earth. The last time the Sun was at this point in its orbit, dinosaurs were just beginning to emerge. The time before that, the supercontinent Pangaea was still intact. Earth has been around for about 20 galactic years. The universe has existed for about 60 galactic years. These timescales are almost incomprehensible. The Milky Way has several distinct regions. At the centre is the galactic bulge, a dense concentration of old stars. This region is about 10,000 light-years across. The stars here are packed much more densely than in our neighbourhood. If you lived on a planet near the galactic centre, your night sky would be filled with thousands of bright stars, making the night almost as bright as twilight on Earth. At the very centre of the galactic bulge sits Sagittarius A, a supermassive black hole. This black hole has a mass of about 4 million times the mass of our Sun. It's relatively quiet now, but it occasionally flares up when gas or even a star falls into it. Around the galactic centre are the spiral arms. These are regions where gas and dust are compressed, triggering star formation. The spiral arms appear bright because they contain lots of young, hot blue stars. Our Sun, being an older, more stable star, has had time to drift away from the spiral arm where it formed. We're now between spiral arms in a relatively quiet region. This is probably beneficial for life on Earth. Spiral arms are violent places with lots of supernovae and intense radiation. Surrounding the spiral structure is the galactic halo, a roughly spherical region containing old stars and globular clusters. The halo extends about 130,000 light-years from the galactic centre. The halo also contains dark matter. We can't see dark matter directly, but we can detect its gravitational effects. The Milky Way's dark matter halo extends even farther than the visible halo, possibly out to 600,000 light-years or more. Most of the Milky Way's mass is actually dark matter, not stars and gas. The Milky Way isn't isolated. It has numerous satellite galaxies orbiting it. The two most famous are the Large and Small Magellanic Clouds. Both are being slowly torn apart by the Milky Way's gravity and will eventually be completely absorbed. The Milky Way is also moving through space toward the Andromeda Galaxy. In about 4.5 billion years, the two galaxies will merge into a single large elliptical galaxy. And Earth? At this scale, Earth is beyond insignificant. The entire planet would be so small that no measurement could capture how tiny it is compared to structures like the Milky Way, galaxy clusters and superclusters, the cosmic web. The Milky Way isn't alone in space. It has neighbours. About 50 galaxies, including the Milky Way, form what astronomers call the local group. This is our immediate cosmic neighbourhood. The largest member of the local group is Andromeda, also called M31. Andromeda contains about 1 trillion stars, more than twice what the Milky Way has. It's about 220,000 light-years across, more than twice the Milky Way's diameter, and it's on a collision course with us. In about 4.5 billion years, Andromeda and the Milky Way will merge into a single large galaxy. Don't worry about the collision, though. When galaxies merge, the stars are so far apart that actual collisions between stars are incredibly rare. The next largest member of the local group is Triangulum, or M33. It contains about 40 billion stars and is about 60,000 light-years across. The rest of the local group consists mostly of dwarf galaxies, small collections of a few billion stars or less. The local group spans about 10 million light-years. That sounds enormous, and it is. But it's just the beginning. The local group is part of the Virgo Supercluster, an enormous collection of galaxy groups and clusters spanning about 110 million light-years. The Virgo Supercluster contains at least 100 galaxy clusters and groups, with a total of somewhere around 100 trillion stars. The dominant structure in the Virgo Supercluster is the Virgo cluster itself, located about 54 million light-years from us. This cluster contains between 1,200 and 2,000 galaxies. M87, a giant elliptical galaxy at the heart of the Virgo cluster, contains about 1 trillion stars. It's roughly 120,000 light-years across, similar in diameter to the Milky Way but much more massive. M87 is also famous for being the first galaxy where we directly imaged a black hole. In 2019, the Event Horizon Telescope collaboration released an image showing the shadow of M87's supermassive black hole. Consider this, magnitude for a moment. The Milky Way seemed enormous, but it's just one galaxy in a cluster that contains thousands, and that cluster is just one part of a supercluster that contains hundreds of clusters. If we made a scale model where the Milky Way was the size of a coin, the Virgo supercluster would be about the size of a large city. Everything you've heard about up to this point, the Sun, the solar system, the distances between stars, the Milky Way itself, all of that would fit on a coin in this model. And Earth? Earth would be far smaller than any particle you could see with a microscope. In 2014, astronomers discovered something even larger than the Virgo supercluster. They found that the Virgo supercluster is just a small part of an even more massive structure called Laniakea. The name comes from Hawaiian and means immeasurable heaven. Laniakea is a supercluster of superclusters. It contains about 100,000 galaxies spread across 520 million light-years. All these galaxies, including our Milky Way, are slowly moving toward the center of Laniakea, pulled by the combined gravity of all that mass. The center of Laniakea, the point toward which everything is flowing, is called the Great Attractor. This is a region of space with such enormous gravitational pull that it's drawing in thousands of galaxies. At this scale, the Milky Way has become just one of 100,000 galaxies in Laniakea. And Earth? Picture the observable universe scaled to Earth's dimensions. The Milky Way would shrink below atomic scale, and Earth itself would cease to exist at any measurable size. When you map out the distribution of galaxies across the universe, a pattern emerges. Galaxies aren't randomly scattered. Instead, they cluster along filaments and walls, forming a cosmic web. Between these filaments are vast empty regions called voids. This structure exists because of how the universe evolved. In the very early universe, tiny density fluctuations existed in the distribution of matter. Over billions of years, gravity amplified these differences. Dense regions attracted more matter, becoming denser. Less dense regions lost matter to their surroundings, becoming voids. The result is the cosmic web we see today. Filaments of galaxies stretch across hundreds of millions of light-years, surrounding voids that are nearly empty. One of the largest known structures is the Sloan Great Wall, discovered in 2003. This is a wall of galaxies stretching about 1.37 billion light-years. It contains tens of thousands of galaxies arranged in a relatively thin sheet. Another large structure is the Hercules Corona Borealis Great Wall, which might be the largest structure ever discovered. It stretches about 10 billion light-years across. That's about 73% of the radius of the observable universe. Between these structures are the voids. The largest known void is the KBC void, about 2 billion light-years across. Inside this void, there are very few galaxies. These voids make up about 80% of the universe's volume. Most of space is empty. The galaxies, superclusters and filaments occupy only a small fraction of the total volume. And our world's significance here? Earth sits in one of these islands in a galaxy that's part of a filament in this cosmic web. At the scale of the cosmic web, Earth doesn't just become invisible, it becomes inconceivable. The observable universe and beyond, the observable universe is the part of the universe we can theoretically see. It's limited by the speed of light and the age of the universe. The universe is about 13.8 billion years old. You might think this means we can see 13.8 billion light-years in every direction, but the universe has been expanding the whole time. Space itself has been stretching. The result is that the observable universe is about 93 billion light-years in diameter. That's the maximum distance from which light has had time to reach us, accounting for the expansion of space. Within this observable universe, astronomers estimate there are about 2 trillion galaxies. 2 trillion. Each containing anywhere from millions to trillions of stars. The total number of stars in the observable universe is estimated at around 200 billion trillion. For comparison, if every star was represented by a grain of sand, you would need several Olympic-sized swimming pools to hold them all. And Earth? Earth would be so unimaginably small that no comparison captures it. With the observable universe scaled to Earth's dimensions, the Milky Way shrinks beneath subatomic particles, and Earth transcends measurability entirely. It would be smaller than the fundamental particles that make up atoms. The observable universe is just what we can see. The actual universe is almost certainly much larger. How much larger? We don't know. It might be a few times larger than what we can see. It might be thousands of times larger. It might be infinite. If the universe is infinite, then the observable universe is basically nothing. No matter how large 93 billion light-years seems, it's still 0% of infinity. And Earth would be even less significant in an infinite universe than it already is in the observable universe. Some theories in physics suggest the universe might be part of a multiverse, an infinite collection of universes. According to eternal inflation theory, the Big Bang wasn't a single event but something that happens constantly, creating bubble universes that spawn more bubble universes. If the multiverse exists, then our entire universe, with its 93 billion light-year diameter and 2 trillion galaxies, is just one universe among infinitely many, and Earth becomes even more vanishingly insignificant. What makes Earth special? Despite its infinitesimal size, the universe operates on principles of physics and chemistry that are the same everywhere. Stars form, burn, and die according to universal laws. Planets coalesce from dust and gas through gravitational attraction. Yet Earth stands apart in one crucial way. It harbours something that might be extraordinarily rare or even unique: the emergence of complexity from simplicity, the organisation of matter into living systems, and most remarkably, the evolution of consciousness capable of comprehending its own cosmic insignificance. Think about that paradox for a moment. We're standing on a planet so small it essentially doesn't exist at cosmic scales. Yet from this vanishing point we've managed to measure and map the entire observable universe. How did unconscious matter organise itself into conscious observers? How did atoms, following blind physical laws, arrange themselves into beings capable of wonder, of asking questions about their own existence? The fact that you're reading these words right now, understanding them, contemplating your place in the universe, is perhaps more remarkable than any of the vast structures we've discussed. Earth might be tiny, but it has accomplished something that billions upon billions of other worlds apparently have not. It has produced a biosphere, an interconnected web of life spanning millions of species. It has produced intelligence capable of technology, of art, of science. It has produced beings who can look up at the night sky and, through nothing but thought and observation, determine that those points of light are actually distant suns. This brings us to a sobering realization about responsibility. If life is rare, if consciousness is even rarer, then what happens on Earth takes on cosmic significance. We are quite possibly the universe's only way of knowing itself. Through us, through our observations and our science, matter has become aware of matter. The universe has produced structures, us, capable of understanding the universe. Every species that goes extinct on Earth isn't just a loss for our planet, it might be a loss for the entire universe. Every potential future where humans fail to survive and spread isn't just a tragedy for our species. It might mean the permanent silencing of the universe's ability to comprehend itself in this corner of space. The Fermi paradox. Where is everybody? Given the enormous size of the universe and the vast number of stars and planets, a question naturally arises. If life is possible, shouldn't it be common? And if life is common, where are all the aliens? This question is known as the Fermi paradox, named after physicist Enrico Fermi, who reportedly asked, "Where is everybody?" during a lunch conversation in 1950. The paradox is this: the universe is old and vast. Even if intelligent civilizations are rare, there should be many of them scattered across the galaxy. Some should be millions or billions of years older than us. They should have had time to colonize the galaxy. So why haven't we detected any sign of them? There are many proposed solutions to the Fermi paradox. One is that intelligent life is incredibly rare. Maybe the jump from simple life to complex life is extremely difficult. Maybe intelligence rarely develops. Maybe technological civilizations tend to destroy themselves shortly, after developing advanced technology. Another possibility is that civilizations exist but are staying quiet. Maybe they've learned that broadcasting your presence is dangerous. Maybe they're deliberately avoiding contact with other species. Or maybe civilizations exist but communicate in ways we can't detect. We've been listening for radio signals, but maybe advanced civilizations use something else. Quantum communication, or technologies we haven't imagined yet. Another sobering possibility is that space is simply too big. Even if civilizations are common, the distances between stars are so vast that contact is effectively impossible. A radio signal travelling at the speed of light would take years, decades, or centuries to reach even nearby stars. The galaxy might be filled with civilizations that will never meet because the distances are too great to cross. This isolation is one consequence of Earth's smallness. We're tiny, and we're separated from other potentially habitable worlds by vast gulfs of empty space. Even if life exists elsewhere, we might never know. How we came to understand our place. It's worth reflecting on how we came to understand all this. For most of human history, we had no idea how small Earth really is. Ancient people believed Earth was the center of everything. The sky was a dome overhead with lights fixed to it. The sun, moon, and planets moved around us. We were special, central, important. This geocentric view made sense based on observation. When you stand on Earth and look up, it certainly appears that everything revolves around us. Greek philosophers like Aristotle developed elaborate models of the cosmos with Earth at the center. This geocentric model dominated Western thought for nearly 2,000 years. The first major challenge came from Nicholas Copernicus in the 16th century. Copernicus proposed that the Sun, not Earth, was at the center. Earth was just another planet orbiting the Sun. This heliocentric model was simpler and more elegant than the geocentric model, but it was controversial. It challenged deeply held beliefs about humanity's place in the cosmos. In the early 17th century, Galileo Galilei provided evidence for the heliocentric model. Using one of the first telescopes, Galileo observed the phases of Venus, showing that Venus must orbit the Sun, not Earth. He also discovered 4 moons orbiting Jupiter, proving that not everything orbited Earth. Galileo faced opposition from the Church. He was tried by the Inquisition in 1633 and forced to recant his support for heliocentrism. He spent the rest of his life under house arrest, but the evidence was clear. The heliocentric model gradually gained acceptance. Earth was no longer at the center of the cosmos. In the early 20th century, astronomer Harlow Shapley studied globular clusters and determined the size and structure of the galaxy. He showed that the Sun was not at the center of the Milky Way. We were about 2/3 of the way out from the center. In the 1920s, Edwin Hubble made an even more profound discovery. He observed galaxies beyond the Milky Way and measured their distances. This showed that the Milky Way wasn't the entire universe. It was just one galaxy among many. Hubble also discovered that galaxies are moving away from us, and the farther away they are, the faster they're receding. This led to the Big Bang theory. Each discovery has reinforced the same message. The universe is vast, and Earth is tiny. The pale blue dot. In 1990, the Voyager 1 spacecraft, which had completed its primary mission and was heading out of the solar system, turned its camera back toward Earth and took a photograph. Earth appeared as a tiny pale blue dot, less than a pixel in size, suspended in a beam of sunlight. This photo, taken from about 3.7 billion miles away, is one of the most profound images ever captured. It shows Earth as it really is in the context of space, a tiny speck floating in an enormous void. The astronomer Carl Sagan reflected on this image in his book Pale Blue Dot. He wrote about how every human who ever lived out their entire life on that tiny speck. Every king and peasant, every hero and villain, every creator and destroyer of civilization, all of them lived on that dot. All our triumphs and tragedies, all our wars and peace, everything that has ever mattered to humanity happened on that barely visible speck. Sagan's point was that this perspective should change how we see ourselves and our world. The petty disagreements that divide us, the borders we fight over, the resources we compete for, all of it plays out on a stage so small that from a modest distance, it disappears entirely. This doesn't make our lives meaningless. If anything, it makes them more precious, because as far as we know, that pale blue dot is the only place in the universe where life exists, the future of Earth and humanity. What does the future hold for Earth? In the short term, the next few million years, Earth will remain largely as it is. The continents will continue drifting slowly. The climate will change, but Earth will remain habitable. In the longer term, about 1 billion years from now, the sun will start to heat up as it ages. The oceans will begin to evaporate. Earth's surface will become increasingly inhospitable. In about 5 billion years, the sun will exhaust its hydrogen fuel and begin fusing helium. It will expand into a red giant growing so large that it will likely engulf Mercury and Venus. Earth might survive on the outer edge of the sun's expanded atmosphere, but it will be a scorched, lifeless rock. Eventually the sun will shed its outer layers and become a white dwarf. Earth, if it survives, will orbit a small, dim star that provides no warmth. But that's billions of years away. For now, Earth is a vibrant, living world, the only world we know that's teeming with life. And there's another future to consider, the future of human exploration. If humans survive and continue to develop technology, we might one day leave Earth. We might establish colonies on Mars, on the moons of Jupiter and Saturn, perhaps even in orbit around other stars. If that happens, Earth will remain important as our birthplace, but it won't be our only home. But even if we spread throughout the galaxy, even if we eventually inhabit thousands of worlds, the scale of the universe will remain humbling. The Milky Way is just one galaxy among trillions. Conclusion: small but precious. We've covered enormous distances tonight. We started with Earth and zoomed out, comparing it to larger and larger structures until we reached the observable universe itself. And along the way, we discovered something profound. Earth is small. Smaller than most people realize. When you compare it to stars, galaxies, and cosmic structures, Earth becomes so tiny that it almost disappears from view. If you made a scale model of the observable universe, Earth would be far smaller than an atom. It would be smaller than anything you could possibly see or measure. It would be, for all practical purposes, non-existent. But Earth is also home. Every human who's ever lived has lived here. Every thought, every emotion, every achievement, all of it happened on this small planet. Earth might be tiny in the cosmic sense, but it's everything to us. And here's the remarkable part. We can understand this. We can comprehend, at least intellectually, how small we are. We can look out at the universe and grasp its scale. That's extraordinary. That's what makes us special. Out of all the planets in all the galaxies, Earth is the one that produced beings capable of understanding the universe. We might not be alone in this. There might be countless other civilizations out there, looking up at their own skies and wondering about the cosmos. But we don't know that for certain. Right now, Earth is the only place we know where conscious life exists. That makes Earth precious beyond measure. Size doesn't determine value. What matters is what's here. And what's here on this tiny planet is something remarkable. Life, consciousness, the ability to wonder, to question, to seek understanding. So yes, Earth is small, but it's also irreplaceable. It's the only home we've ever known. And in a universe that's vast and mostly empty, a small world full of life is something to treasure. The next time you look up at the night sky, remember what you've learned. The stars. You see a part of the Milky Way, our home galaxy. Those stars are suns, many with their own planets, and our galaxy is just one of trillions scattered across an almost unimaginably vast cosmos. Earth is tiny in all that vastness, but Earth is also home, and that matters more than size ever could. Thank you for joining me on this journey across the cosmos. If you found this exploration meaningful, please consider liking this video and subscribing to the channel. Your support helps me continue making these deep explorations of space and our place in it. And remember, you're standing on a planet that's tiny beyond comprehension when compared to the universe. But you're also standing on the only world we know that's home to life, consciousness and wonder. That's something to celebrate. Sleep well tonight, knowing that you're part of something vast and beautiful. The universe is enormous, Earth is tiny, but Earth is precious. And you, living on this small world, are part of its story. Good night,